Hello.
Hello, good afternoon.
Hi, can you hear me? Hi, this is
Yes,
Jian Wang from Nvidia. Is
yes,
this Mr. Shaw, Alan Shaw?
yeah, Alan Charles speaking. How are you?
Okay, good. I'm okay.
Thank you.
And I just want to confirm with you that this interview is for fundamentals of deep learning.
Yes,
Okay. Let's go through some of the key points together.
yeah,
Okay, let's start from part one, in which we reviewed the history of AI, and we point out a key difference between expert system and deep learning. What is that key difference?
I think the expert system is a system that we need to use human being to do some coding. So in order to build in all the human experience and knowledge, so you need to take a lot of manpowers and time. And but yeah, this is the problem of the expert system. Yeah. So the expert system is something that if there's something that is not covered before or is not input by the engineers or expert before, then it does not know what to do. Yeah.
What about deep learning?
Yeah.
How does deep learning learn to, for example, recognize the objects in the pictures in the images?
Um, I
The
think
difference. My question was about the difference. You talk about the expert system. That is fine. But I'd like you to describe the difference between expert system and deep learning.
okay. So for deep learning, it's a system that does not need explicitly programming by human beings or engineers. Yeah, while expert system need to can only do with the expert input.
And how does deep learning model recognize the objects in the images, for example?
You mean the algorithm or what?
No, because you said that in order for an expert system to, let's use image classification as an example. Okay, and with expert system, as you said, we have to, the programmers need to build up the knowledge based on the expert
Yeah.
experience, and turn this knowledge into programs code.
Yes.
This is how expert system does. But what about deep learning? How does deep learning learn to recognize the different objects in the images?
So I think it's like a classifier or classification approach. If we show the model the examples, like for example with the photo, if it's a cat or a dog, so we need to give some photos of the cat and dog and the bodies. So the model will take some guess and then we will tell them it's right or not right, and then gradually we will do some we will give them the answer, tell them, oh, if this is right, then it's right, and then gradually the model is learning to correctly categorize the based on the training, and then I think it's like a validation process, training and then validation, and then finally test. This is 3 steps process. Yeah.
Okay, so deep learning learns to recognize those objects from examples, as you said.
Right. Learn from examples. Yes.
From data.
Yes.
And okay, let's talk about the first lab exercise, in which we build a model to recognize handwritten digits, and we provide a data set called MNIST. However, we need to pre-process the data before we send the data into the model to train the model. And one of the pre-processing steps is to apply the so-called normalization to the input images, by which we reduce the pixel value range from 0 to 255 down to 0 to 1, right? So what is the benefit of applying normalization to the input images?
I think normally I think we call this like I mean in the industry we call it a data cleansing process, or pre-processing of the data. So the normalization of the images will help to improve the speed of the training of the data for the model, and then it will also be help to make the model easier to train, since the data is scaled to between 0 to 1 instead of a 0 to 255. So and as there are lots of different scales, so I think the model can converge to the local minimum faster during the process of training the model and the network.
Okay, gotcha. And another pre-processing step is to convert the original labels from integers to one-hot encoding. And again, why is the step necessary?
I think because not many algorithm can work with this type what we call the categorical data. So only if we apply to convert the categorical data into a one-hot encoding, then that will become more expressive. Otherwise, it's very difficult to work on that.
Okay. We provide a counterexample in the notebook, which basically illustrate the problems if we do not make this conversion. If we use the integers 0 to 9 as the label, what the problem would be. We provide an example in the notebook. If you can read it, you may have another explanation for why it is necessary to make this conversion. Okay?
Why we need to make the conversion?
I mean, yes. Why do we need to make this conversion from integer-based labels to one-hot encoding? I mean, what you explained was okay, but we also provide an example in the notebook of this lab exercise that could better illustrate the necessity of this conversion. I just suggest you to read carefully the contents in the notebook, Jupyter notebook, to find that example, so that you have something that you can use to explain to your student.
Okay, understand. I think that's something.
Yeah, your explanation is okay. You said that it has a better description of the categorical data. That is fine. I'm not saying that your answer is wrong, but I just suggest you to find that particular example in the notebook, so that you may have something else to use to explain to your students. We provide an example that explains the problem. You know, if you do not convert the integer label to one-hot encoding, what the problem would be.
So that's another example, right?
Another example, I said it's a kind of a counter example.
Okay.
From the opposite direction, to say that if you do not make this conversion, you may have this problem. Okay.
Understand. Thank you for your advice.
All right. So after we make this conversion for classification models, what is the loss function we usually use for classification models?
What's the loss function?
Yes. What is the loss function we usually use for classification models?
The
name of the loss function.
Cross entropy.
Yes, cross entropy. That's right. And let me give you a use case, a good example in which a student wants to build a binary classification model. You know, in part 5, we will build a model for binary classification to identify a common animal, whether the common animal is a dog or not a dog, right? Yep. Remember that? That is a typical binary classification problem. And now a student wants to build a binary classification model, but based on what he learned from the first lab exercise, he puts 2 neurons in the last layer of the model. 2 neurons. because in the first lab exercise, we tell students that the number of neurons in the output layer of your model should be equal to the number of classes. So that is why he puts two neurons in the last layer, the output layer. And in this case, what is the type of cross entropy should the student use as the loss function? I'll give you two options. One is binary cross entropy. The other one is categorical cross entropy. Which one should the student use for his case?
I think it's not binary, because for binary there should be only one neuron, because one neuron can represent 0 and 1. So I think the answer should be categorical cross entropy.
Yeah, that's right. And when you use, yes, that's right. But when you use categorical cross entropy, just remember to convert the label to one-hot encoding. But very likely the original labels are either 0 or 1.
Yes.
And if categorical cross entropy is used as loss function, then the labels should be also converted to one-hot encoding. All right. And in the second presentation, we introduce how a model can be trained by gradient descent. So basically, the training process is like an optimization process. And we have a slide there that says it's better to introduce momentum to the optimizers. And what is the purpose of introducing momentum?
You mean the purpose of introducing the momentum into the process? Oops. Hello.
Hello,
Mr. Wang.
Yes. Okay. Welcome back.
Sorry for some problem with the
Yeah, it happens.
network.
No problem. It happens. So I'm gonna share with you. I was just asking you about momentum, introducing momentum to optimizer, and I'm gonna share the slide with you. You can see here. So my question was about the benefit of introducing momentum to optimizers.
Yes.
Could you explain the benefit of introducing momentum to optimizers? Can you see my slide?
Yes, I can see.
Okay,
So I think the gradient descent is like a ball rolling down to the slope of the mountain, and like a bowl, and to the bottom of the bowl. But the area is the lowest at the lowest point, or we call the local minimum. Okay, but as we can see from this diagram, there are some ups and downs of the heel of this bow or this heel. So and the up and down will make the ball cannot go to the real minimum, or we call the global minimum, unless we have a momentum to push the ball to pass the throws or the ravine, so that it can go to the real minimum, or what we call the global minimum. So if the momentum, the automatic process may not be able to really process and get the real lowest point, which is the lowest error.
Okay, that's good enough. By the way, do you know how momentum is calculated?
I think it's calculated based on the moving average of the gradients, or the past historical gradients, something like that.
Yes, that's right. All right. And also in this presentation, we introduced a key concept of overfitting. And we know overfitting is a bad thing. So is there a way to tell whether overfitting is taking place during training, not after, but during training, in the course of training? Can we tell when overfitting is taking place?
Because during the training, normally the loss will go downwards, but if the validation go upwards to the opposite direction, then I think this is what we call overfitting.
All right, that's right. Okay, that's about the second presentation. Let's move on to part 3, which is about CNN, convolutional neural network. I'm gonna share with you a slide again there in the third presentation. Just give me a moment. All right. So this whole presentation, the entire presentation is about CNN. This slide shows the feature maps, and here we go. We have this slide, which looks fantastic, but also very confusing. How would you present this slide to the student? What is the key message of this slide you'd like to deliver to your students?
I think I would say we need to have a lot of dogs photos or images, and because all the photos will contain different features of dogs, and the model will use the filters to train the image on the left hand side, and then we'll tune the pixels of the input image, and the image will become group all the features together and generalize it. So, and then that will become like a activation to the CNN networks.
And the purpose of this process is to demonstrate what?
To demonstrate. What's your question? Sorry,
No, you described correctly the way that we turn the picture on the left to the picture on the right.
Yes.
That is fine. So what is the purpose of doing this?
Because we need to, like I said earlier, I think the photos contain the features of dogs. Okay. That a human being can see as a dog. So a dog has, or dogs has have many different features: the ear, the hair, the eyes, the nose. So we would like to demonstrate how the neural network, the CNN, to how it's so powerful that it can extract, or to how to say, to filter, or to collect, or to to get out all the features of the dogs from the totals, and then just like we generalize it, and then it will pass like to the right hand side, the photo at the right hand side, to show what does a dog looks like.
Okay. Just want to make a comment here.
Yep.
The way that it's described, to, turning a picture from left to right, uh, provides a very efficient and compelling um, evidence that CNN is very good at learning features. And this approach is also a way to visualize the features within the CNN network. So it's a feature visualization method that can really demonstrate the features within the network, within the CNN model that people, I mean, human being can understand. Otherwise, it's really difficult to visualize the features in the model that has been trained. Okay, so and this project is called Deep Dream. Probably you can mention that to the student. Uh,
Yep.
Deep Dream, created this very innovative way to visualize the features within a CNN model.
Understand.
All right.
Understand.
And we also tell students that within the CNN network, we can insert other types of layers between two convolutional layers, such as pooling layer and dropout layers. So pooling layer, I think, is straightforward to understand. Regarding dropout layer, we know the purpose of inserting dropout layers is to help the model to kind of avoid overfitting. But could you explain how dropout could help avoid overfitting?
Because the dropout randomly turns some neurons to zero, and because if all the neurons are working together, that might create something very complicated functions, and they might be increase the chances of picking up all the noises in the training data. So if we randomly drop out some neurons, that means turn them into zero, then they will be unable to work together and cannot collect, or to how to say, cannot create some really complicated functions, and that means that no more noises or some irrelevant stuff will not be collected from the training data, and that finally will lead to the effect of preventing the overfitting.
Mm-hmm. So you think that if a model overfits the data, it will learn something from the noise in the data, or I think if you say the model is too good to even fit the noise in the data, that is understandable. But is that what you just said?
Hello. Hello. Hello.
Yes, I just
Okay.
want
Sorry.
to. Can you hear me?
Yeah. Now. Okay. Now. Okay. You was.
Okay. Yeah, I think I get your point, but I just want to repeat what you said. You said that with dropout, it makes the model hard to fit the noise in the data. Is that what you just said?
Um. Maybe I don't express myself very well. I mean, what I want to say is, because of the if we have too many neurons and too many parameters,
Mm-hmm.
inputting to the model, then that will have a chance to increase the noise. Okay, so if we turn off some neurons to zero, then their interaction will be minimized, and then that will avoid the overfitting happen.
Okay. I think the core idea of your explanation is to reduce the complexity of the model. Is that
Right,
is my understanding correct?
Yes,
Okay.
yes.
Okay. All right. So that's about part 3. Part 4, we talk about data augmentation. I don't have any questions there. I just want to uh, I'd like to when I present part for data augmentation, I'd like to remind students not to overuse or abuse the techniques that we teach them in the lab exercise. That means that whenever you create new images based on the current existing images, do not shift or rotate the existing messages in a large range. Keep the range small, and so that we do not create something that even human being cannot recognize. Okay, that's my
Understand.
suggestion to the students. All right,
Thank you. Thank you.
let's move on to part 5. We talk about transfer learning, and there's one key concept in transfer learning, which is fine-tuning. Fine-tuning. Could you explain to student what fine-tuning is?
We will unfreeze the whole model, the whole the complete or the entire model, and we will train it with a very small learning rate so that the original training result can be kept, and this will also be able to cause the base pre-trained layers with a very small steps learning rate, and we can adjust it as in a very small step by step, but not in a very big jump. So we will improve the model by a little amount.
Okay. All right. Yes, we must use very small learning rate. There are good reasons for doing so. For example, when we unfreeze the base model, the model becomes very large. But we have a small data set, Obama's dog, it's a small data set. It's very easy to go overfitting, large model over a small data set. That's a typical scenario where overfitting can take place. And also, we want to keep the features that the base model has already learned from pre-training, right? So we do not want to change the weights in the base model significantly. So there are some good reasons behind using small learning rate.
Right.
Okay. All right. Let's
Understand.
move on to the next part. Yeah, the next part is about NLP. Because this is fundamentals of deep learning, we'd like to cover not just computer vision tasks, but also a little bit natural language processing. And first of all, could you give your students a few application examples of NLP?
There are quite a lot, but
Yes.
I think most common that we will encounter on our daily life are like spell check and like search engines, spam email filtering, and or like a translation dictionary, Google what they call Google Translator. Yeah, all these are very typical and easy understandable examples for the students, I think.
Okay, good enough. And so the first part of this, the first section of this part is about how to convert text into numbers, I'd say. So it's about text representation, and the process is called tokenization. So what do we expect out of the tokenizers? When we send a sentence to the tokenizer, what do we expect out of the tokenizer?
I think the words are like a book or dictionary or a magazine with a lot of unique words. They may be put in alphabetical order or something like that, and then we need to have like a hello.
Yes, go ahead. I just
Okay. Because
Yeah.
I lost the photo.
No, it's
lost the PowerPoint.
slide.
Okay.
Yes.
Okay. So and then it's like a book. We have the index on every page at the front page. After like the preface, and then we have the index. So the index can tell you which page is about which topic or which chapter. So like a dictionary, when you have the number of index from 1 to 10, for example, then there will be a corresponding words, unique words, like in the dictionary, so that when we are using the number, the tokenization is that we separate the piece of text into like a small token or small pieces of wordings, and then we assign the number to match the individual or unique words. So we expect the numbers will represent the words from this like book or dictionary or whatever. So yeah, this is what we expect. What a tokenization carries out.
Okay. And after tokenization, we actually get the initial representation, I mean, numerical representations of the words, as you said.
Yes.
And then when we send this, so a sentence, a text-based sentence will become a vector with numbers inside, right? And then when we send this vector into the model, we actually send them one by one token after another. And however, we know that these numbers, as you said, these numbers are actually the numbers, the index numbers of the words in the dictionary.
Yes.
These numbers do not have any numerical meanings. For example, if we use 10 to represent word dog and 8 for cat, it does not mean that dog is more important than cat, simply because we use 10 to represent dog, which is larger than 8 for cat, right? So these numbers should not carry any numerical meanings. They only represent the place, the position of the words in the dictionary. So that said, we actually turn these numbers, integers, into one-hot encoding when we send these words into the model. So we have a slide I'm gonna share with you in the sixth presentation. So you can see after tokenization, we have this vector that represents this sentence. But when we send this vector, these numbers to the model one by one, we actually turn them into one-hot encoding. So the number 10, for example, only represent the position of the word in the dictionary. So in order to indicate that position to the model, we turn on the 10th input component to 1, while keeping other components 0, right? And so effectively, this is one-hot encoding. We turn number 10 into one-hot encoding. So basically, this is the representation of text is one-hot encoding. Okay.
Right.
So what are the problems of using one-hot encoding to represent word?
Because human being use so many words, okay? So
Right.
I think the problem is very straightforward. If you have 1 million words, 2 million words, then with one hot encoding, we will have there will be also lots of ways. And in the calculation, when we do the calculations, because there will be 1 million or 2 million dimensions, then the calculation will be very slow or very complicated. So yeah, this is the problem, I think. Yeah.
Another problem you can think of?
Because you also just remind me about that all the numbers has no numerical value or meanings. So same to the words. Sorry. Let me start again. I need to rephrase my word. So as you have mentioned, all the numbers are only represent the position of the unique words, but it does not has any numerical meanings. So that means between the words they have no meaning or no correlation with the other words. So that means how to say? That means there's no synthetic meaning in terms of the language. So that means in reality the words but when we are talking, of course, the whole phrases are meaningful, right? So if they don't contain any synthetic meaning, then that means you cannot distinguish what is the same meaning or opposite meaning. That means synchroms or ennoms. You know what I mean? So means the words with the same meaning or the words with opposite meaning are not be able to distinguish by the one hot label. Hello, hello. Hello, hello. Hello, hello. Hello? I mean, hello?
Hello.
Hello? Hello? Hello?
I'm very sorry.
Hello, Mr.
It's
Wang?
my problem. My network is down. Was just down.
Oh, sorry.
Okay. I'm sorry about that. Let's continue. I was just asking you about another problem with one-hot encoding as the representation of words.
Yes. So my answer was just shortly before the cut down. I was trying to say, like you mentioned, because the numbers correspondent to a unique words, but the numbers they don't have any numerical meaning. Okay. So for that, but in reality, when we are talking, all the words have some syntactic meanings between the words. So that means the words are related to each other. They must have some relationship, okay, or meaning. But if I use the one hot encoding, then you cannot distinguish like synonyms and antonyms. That means opposite words or words with the similar meanings. They cannot distinguish whether it's the same meaning or different meanings or opposite meanings. You can't distinguish.
Okay.
Because with the one hot encoding, they have no meanings. Yeah.
That's right. And also, words have relationship between each other, either semantic or syntactic. There are some relationships. And with the one-hot encoding, we know that the one-hot encoding vectors, they are orthogonal to each other. If you make dot products between two different one-hot encoding vector, the result is 0. So if two words such as dog and cat, they have some relationship, right? And but with one-hot encoding, we cannot represent this kind of relationship between words. And that comes to the next slide, where we come up with the so-called embedding vector. Like you said, with one-hot encoding, the other drawback is that the embedding one-hot encoding vector can be very long. Well, the length is not million, but it is at least the same length as the dictionary. if we have like 30,000 um, 30,000 words in the dictionary, then the length of the 100 encoding vector is 30,000. So in order to address these two problems, we come up with embedding vector. So that is, let me re-share the slide with you. Let me see, where is it? Over here. Okay, this one is a Chinese version, but I just want to use the diagram. So you can see here. So this is the so-called embedding vector. Okay, so with the embedding vector, we can see that two words that represent two similar animals will have close their position in the embedding space is small, while the these two animals, they are not like each other, so their distance in the embedding space is large. Could you hold on, please?
Yeah.
All right, I'm sorry for that. Unicom, China Unicom is calling me to see what the problem is with my network, so I have to pick up his call. Anyway, let's continue. And my question is about the embedding vector. How we can generate this type of embedding vector automatically?
How we can generate the embedding
vectors,
vector.
because we say that we do not like one-hot encoding to represent word. We'd like to use embedding vector. Why? Because embedding vector, it's short. You can see it. This is two-dimensional vector. And another benefit is that we can embed some meanings or relationship between words into the embedding vector. So the two embedding vectors that represent the words that are similar will get closer to each other in the embedding space. So this is a much better representation of words than one-hot encoding. And we can manually pick up the numbers, the real numbers in the vector for each word. But this is certainly not realistic, right? There will be 30,000, even to 50,000 words in the dictionary. So it's not realistic to manually pick the numbers for each word to build their embedding vector. So there should be an automatic way to generate these embedding vectors for the words. So my question is, what is that? Is there any automatic model, any model that can generate this type of embedding vectors?
Do you mean the word-to-vec?
Yeah, for example, word-to-vec. So how does word-to-vec work to generate this type of embedding vectors?
I think word-to-vec has two flavors. One is skip-gram, and that one is the SIBO.
Right.
And then we use a word like center word. as the input and then use this to predict the rest of the sentence or context and or what we call the context words.
Okay, good enough. That's right. That's good enough.
Okay.
You're right. And on the slide, you can see this is an word-to-vec architecture, which looks like an autoencoder. But as you said, we use a center word to predict the context word. Okay. And then after trained, we get the embedded vector from the hidden layer, and usually we just keep this part. This is called encoder, and we connect the encoder to the model. The model is called RNN, and so the next question is about the model we use to implement those NLP applications, and the model is called recurrent neural network. Right.
Yes.
So could you explain to the students why this type of model has to divert the output of RN layer back to the input layer? This is my input layer. Okay. So why do we have to loop back the output of RN layer to the input layer and concatenate this vector with the input vector?
Because we need to know the meaning of the word, the prediction of the word as a relationship with the input word. Yeah.
And
so and because the input word is like what we call, like the previous word we use, we have a very definitely we have the impact on its final prediction. So without doing this recurrent neural network, that by having the prediction, the output words going back to the input word, it can work out like this.
Okay. That's good enough. I just want to add something. We use as an example. If we could you hold just a moment? Sorry.
Sure.
I just want to add something. Use this two sentences as an example. The current word is say. This is the current one. We want to predict the next word. But if we don't look back to the previous word, we don't know whether we need to predict, for example, meow, or we need to predict bark, right? We don't know which one is better. So, but when we look back at the previous words, the context, then we have better idea what the next word should be, right? So in order to look back, we need to divert the output of RN of the previous time step back to the input layer and concatenate it with the current word, say, as the input, the new input to the RN layer. This way we take into account the context, not just the current word. All right, that's my last question. We also have a few slides that introduce the other types of neural network architecture, such as autoencoder, GAN, and reinforcement learning. This is not a model. This is just another way of learning. But I won't ask you any questions. Please get prepared to present these slides very briefly. Make a brief introduction of the autoencoder and GAN and reinforcement learning. That is enough. All right, Alan, thank you very much. So the next step is that my colleague Tanima is going to send you a notification email with the result of this whole certification process. But don't worry about the result. I think you did very well. And I really appreciate your effort and your time and your engagement with DRI. Okay, thank you very much.
Thank you very much.
Thank you. Bye bye.
Thank you. You too. Thank you. Bye bye.